Okay. So this week we are talking about bivariate correlations and bivariate associations. First, I apologize for getting the video up so late. I have been out of town, and I planned on actually getting it up while I was gone. My hotel had horrible internet. I was in College Station. College Station apparently is not Houston. It's actually crazy. Yeah, all of this is going to wind up being on the video, unfortunately. We're flying into College Station from Houston, right? And we get there, and we just start circling. And then eventually the captain comes on, and he was like, unfortunately, we can't reach ground control in College Station. We're going to have to turn around and go back to Houston. They did. They turned around, they went back to Houston. And then as soon as they landed, they said, oh, we're able to reach College Station now. It turns out there was a small fire and all of their they lost electricity. We're going to fuel up again because they give you just enough fuel to like get to where you're going, right? We're going to fuel up again, and we're going to apparently to get to where you're going and get back if you need to. And then we're going to head back over there so they fueled up. It was just weird. Anybody ever had that before where a plane is like, it's like my dad's driving. He's like, shut up back there. I'm going to turn this thing around. And that's exactly what they did. It was a bit crazy. But College Station is a smaller town, and apparently in the hotels, the internet is terrible. So I can get like my phone to work, but my computer, no go. So anyway, we're going to be talking about correlations today. I got the video posted last night. I was dead tired when I did that video, so hopefully it was intelligible. The first thing that we're going to do, though, everybody have their data open now? All right, let's do something really quick. Before we get going, what is a correlation? What is a bivariate correlation? How would you define that? The relationship between two variables. And if you had to define that relationship mathematically, how would you define a bivariate correlation mathematically? What would you say it is? Anybody have an answer to that yet? Not necessarily the formula. There's something easier. There's an easier way to think about it. Like, I'll show you. Jigs, I'm going to come right back to you. That's the formula, right? Like, I don't want you to say that. I don't expect that. Go ahead. What were you going to say?
So, like, in easy terms, we can say what happens to the one variable if other variables increase or decrease.
Yeah, so that's what it is, right? Absolutely, that's what it is. And in fact, that number gives you, what does a correlation coefficient give you? What does that information tell you?
Overlapping SDs.
Overlapping standard deviations, that's exactly what it is. So it is a standardized deviation from the mean. And so that correlation, it doesn't just tell you that there's overlapping standard deviations, right? It tells you how much they're overlapping. And it's a magnitude of a change of one standard deviation in one variable results in a change of R in the other variable, right? And vice versa. So the bivariate correlation is the magnitude of change or overlap in those two standard deviations. You don't have to type this up because all of this is going to be online anyway, so you don't have to worry about it. You can go back and you can rewatch this, and it's more important, I think, that you think about this and you hear it and really digest it than worry about typing. It is so R, an R of 0.4 means that if X increases by one standard deviation, Y increases by what? 0.4, yeah, 0.4 standard deviations, right? If the correlation is minus 0.3 and R increases by one standard deviation, X increases by one standard deviation, what does Y do? Decreases by 0.3. Likewise, if Y increases by one standard deviation, what does X do? Decreases by Great, yeah, right. The relationship is bivariate. It's the same directionally. Okay, so the first thing that I want to do is I want us to let's go. We've got everybody has this data pulled up, correct? Everybody but Becca has this data pulled up. Does anybody else not have this data yet? All right, so let's go analyze, correlate, bivariate. Let's put both of these over here. So you have a few different types of correlation coefficients. You have Spearman for rank, Kendall's tau, which is also similar to or roughly equivalent to phi. Then you have tests of significance, two-tailed versus one-tailed, flag significant correlations. You can leave that checked or uncheck it if you want. I don't care one way or the other. We can get the means and standard deviations. Let's do that. We can also get cross product deviations and covariances. Let's do that. And let's hit OK. So we see that we have 15 people. Our mean is 7.67 for, this is time since PhD. And our mean for publications is 19.93. Standard deviation of 4.577 and 13.833. The correlation between the two is 0.657, right? We're not going to worry about cross products or covariances right now. We will come back to that. So 0.657, and so what does that tell us? Strongly positively correlated, and it tells us something else, right? For every increase of one standard deviation in PhDs, we see an increase of what in publications? 0.657 what? Standard deviation units, right? And mathematically, we can calculate out exactly how many publications this is. If we know that our standard deviation units is 13.823, then one increase in one standard deviation units of time since PhD is how many actual publications? How would we figure that out? So one standard deviation is 13.823, so we would just take 13.823 times.
9.8.
Sure, there we go, right? And you take the standard deviation times the correlation coefficient, and you get the raw number of publications associated with one standard deviation increase in time since PhD, and that is actually time since PhD is standard deviation is 4.577. So that means for every 4.577, we see an increase of 9 point whatever it is, right? Sure. That little bit of math is actually what we're doing when we are running a regression analysis. So let's hop over really quick and let's put this into a regression model. We're going to go analyze, regress, linear. We're trying to predict publications. If you remember from the video, one of the requirements that you need in order to do a regression analysis is you need to know what is the dependent variable, what is the independent variable. In a strictly bivariate regression analysis, the results are exactly the same as they are in a correlation analysis, right? And so if we put these two things in, actually let's do something else while we're here. Let's click on statistics. And we don't need any of that. I'm sorry. Options. Don't need that. Where is it? Save, I bet. There we go. Let's get unstandardized residuals, standardized residuals, unstandardized predicted values, standardized predicted values. Click continue. And you know what? Let's get a plot here. Actually, let's not yet. let's just do this. Hit OK, we run this, and we get our regression model, right? Now, notice that it gives us an ANOVA table, and that ANOVA table has mean squares in it. It has an F value, and it has a significance level of 0.008. That is the main effect of our only predictor in the model, right? And we see it down here as well, 0.008. We have a slope of 1.983. This is an unstandardized slope, right? What does 1.983 mean in this instance? What's that?
Like it's the same thing, like it's the same coefficient. Right?
Yeah.
If it increases by 1, then the
It's
y
an-
will increase by 1.9 times of.
Yes, so in this instance, it's an increase of 1 unit, right? Results in an increase of 1.983 publications. An increase of 1 year since PhD results in an increase of 1.983 publications, right? We also have a constant there, 4.731. What is that? That is the intercept, and what do we mean by the intercept? What is it? The average of what? Huh? Of y. It's not really the average of y, though, is it? What's the true average of y? Somebody grab. Let's do descriptives real quick. Let's go. Actually, did we ask for descriptives up above? We did, I think. The average of y is 19.93. So why is our intercept down here, which is an average of y, why is it 4.731?
That's the dependent variable on the assumed regression line. It's not exact. That's why it's y dash. Might be some other value which we assume on the regression line itself rather than on the real point.
Right. So if we had actually, let's do something else. This is an interesting point. Let's do this. If we go, I'm not sure if SPSS will let me do this, so we will try. If we go linear and we remove, no, it won't let me do it. But you know what will? Theta will, I think. Let's go regress. Time since PhD. Oops, not time since PhD. If we go regress, publications with no predictors, we get only a constant, right? 19.933. That is our average. So the constant in our regression model over here of 4.731 is accounting for the effect of x on y, right? It's removing variance in the mean or variability in the mean that's associated or that's there because of y. So let's do this. We can actually figure this out really quickly. Wrong thing. Okay. Our correlation is, or I mean our equation should be, what's our basic regression equation? Y equals a plus bx, or something along those lines, right? This is, since we're talking about y and not y hat, we're going to say plus error. What is the difference between y and y hat? Let's talk about that real quick. What is y hat? The predicted value, yep. So y hat is the place on that line that we plot that we expect y to be, or we predict y to be. So what is then residual? The difference between y and y hat. Perfect, yeah. Okay, so we have this equation right here. And so let's do this. We have, let's look at our numbers here. 4.731, 1.983. 4.731 is our intercept. Slope was, can somebody read it to me? No? 1.983. 983 is our slope. And so we need one other thing for this equation here, right? We need x. And in this case, we need the average x. So let's go mean x. What is our mean of x? Do we need to flip back over here and have a look? It was up at the top here. 7.67. 0.67. Okay, so if we plug these values in to our regression equation, we have equals, if we're trying to find y, this value plus this value times this value, right? Because remember, your regression equation is the average effect. And so that intercept is going to be controlling for the average effect of x. And we get this. And there's a little bit of rounding error there, right? But that is what? That is the true mean of y, right? So our actual intercept is the mean of y partialing out the variance associated with y due to x. Make sense? Now this partialing out of variance, I think, is an interesting point. Let's do this. So we have this formula, right? And this formula doesn't just apply to R. It's going to apply to every single, in a slightly different form, every single coefficient that winds up going into a regression model. And we're going to calculate R today using this little bit of data that we've got. But I hate doing it using this ridiculously long formula, because I think it's more, I think it drives the point home more if we talk about what R really is. And we said that R is the overlap in standard deviations, right? So in order to look at the overlap in standard deviations, we need to convert our scores into standardized scores, also known as, say that again? Z scores. You must be a Canadian. Somebody's, are you a Canadian? Huh. Yeah, there is a Canadian artist that, no, I don't think so. That says from A to Z in one of her songs. Is it? It's not Shakira. Shakira's not Canadian.
Shania?
No, it's not Shania Twain. But it might actually be Shakira. I don't know. Anyway, I crack up every time I hear it. I think Torre says Z, right? Do you say Z instead of Z? Yeah. Apparently it's the right way. Anyway, yes. So we need to let's start today. I'm going to show you that there is a much easier way to calculate the regression coefficient than this formula right here, or the correlation coefficient, which is also the regression coefficient. Before we do that, just as a point of emphasis, this is our correlation coefficient between publications and PhDs, right? And if we look down at our regression analysis, we see that this is our unstandardized coefficient. Here's our standardized coefficient. It is exactly the same as our correlation coefficient, right? Because in a bivariate analysis, your regression coefficient, your standardized regression coefficient, is the same as a correlation coefficient. And in a multiple independent variable analysis, when you start adding additional independent variables, this is not the case. That they will vary a little bit because there's actually, does anybody know there is one instance when they will always be the same? When would your unstandardized, and this is getting ahead of myself, this is next week, but when would your unstandardized or your standardized coefficients in a regression analysis with multiple independent variables always match your bivariate correlations? Jigs?
When we have a mean of 0 and ST of 1 in all the variables?
Not quite.
If all the variables are measured the same way?
No. You would have the standardized correlation coefficients and the standardized regression coefficients would match perfectly if there was 0 overlap between your predictors. It's almost never true, so it's probably not something that you'll have to worry about. But and we're going to talk about how we examine this overlap here in a second. And I think that the way that we're going to do this makes all of regression leading all the way up to interactions and mediation make more sense. So let's do this. The Excel file that we have, let's start with this. I'm going to move that over. Whoops. Let's compute Z of TS-PhD and Z pubs. Everybody's in Excel now? How do we calculate Z of PhD? How do we make these into a Z-score? What is the first thing that we need to do to make a Z-score? Z-score, what are the two primary characteristics of a Z-score? They have a mean of what? 0 and a standard deviation of 1. Perfect, yeah. So in order to make these into Z-scores, we have to know two things, right? What do we need to know in order to make these into Z-scores? We have to know what the mean is, because we're going to have to subtract every score from the mean in order to get the mean to 0. And we have to know what the standard deviation is, right? So that we can divide everything by that standard deviation, which will put the score at a standard deviation of 1. So let's do this. We need mean PhD, mean pubs, SD PhD, SD pubs. Can somebody look at the data and tell me what the mean is for PhD? I can tell you right now that the mean for pubs is 19 point something or other because it's right here. 7.67. Mean for pubs 19 point what? 93. What is the standard deviation for pubs or for PhD? 4.5. What was this call it? 5.8. Make it easy. And what is the standard deviation for pubs? Louder, please. 13.82. Okay. So in order to calculate a Z-score for PhDs, we're going to put equals, parentheses, this value minus what? Minus our mean, right? And let's add dollar signs in there. That will hold that constant, hold this one constant. Okay, divided by what? this right here, right? And then let's also put dollar signs in here to hold that constant. And then we can grab this and just drag it down. And so if we go, oh, I don't know, anybody familiar with this? I think you might actually, oops. Shoot, what was this value that I just deleted? Anybody know? 18? Okay. You know, equals, I think I need to put average here, right? If we do this, gives us an average of 7.6. So that's our average here, right? And if we go equals, I think it's just SD. No, is it stdev?
Yeah.
That gives us our standard deviation right here. And now we can just grab this and pull this over. That gives us our mean there, our standard deviation there, right? When I grab this and pull this over one more, what should it say? What should my mean here be? 0, right? And why should it be 0? And why should it be 0? It's a z-score. That's pretty close to 0. It's not perfect, right? Actually, if we go like this, and instead of A2, we go, well, oops, nope. Let's not do that. Oh gosh. If we go, we should be A2 minus H9 was 7.67. So if we go that minus actually this, so that, yeah, I know. So that we're not running into, come on, just put it in there for me. A17 and A18, right? And then we grab this and drag it down. It will be a bit more accurate here, and we will get a perfect 0. Do you see what I did there? Or no? Okay, so we had these rounded off means and standard deviations. I just used the more accurate means and standard deviations that we calculated over here. If I grab this formula and I pull it over, what should this value here be? 1, right? Should be 1. And it is 1. Ta-da! All right. Now, if we want to get our z-score of publications, how do we do that? Let's calculate our z-score of publications. We put equals what? This value, right? Oh, we should probably put this in parentheses. This value minus what? Minus what? Yeah, 1993. And let's put in our things here. Divided by what? That, yep. Okay. We pull this down. Now we have all of our publications in terms of z-scores. And if I grab this and pull it over, what should this value right here be? Should be 0. Let's do it. And what should this value right here be? Should be 1. Okay. The thing that I'm going to tell you next is what underlies the basis of all regression analysis. And that is that the relationship between any two variables is the product of their standardized, the product of the two standardized variables divided by n minus 1, which means it is the mean product of two variables, right? In terms of regression, if you think about, this is not going to be, unfortunately, in the video. The relationship between two variables is this. This overlap and that overlap is really the average product of the two variables. We won't work out the proof for that, but you're going to have to trust me for just a second here. And when we start looking at multiple variables, what happens, and we'll talk about this next week, is this gets removed from the equation as a portion of the variable. And this becomes, it's called a partial correlation, right? And then the IV1 and IV2, the relationship is this for IV1 and why this, this for IV2. And those wind up being actually the average products, removing the product of these two, and the product of all three. Eventually, you will find out that this little spot right here is actually represented by what we call an interaction. That's basic moderation. We will get there. We're not there yet. So let's do this. Let's look at the product of our two z-scores. What is a product? Say that again. Multiplication. It's very simple, right? So the relationship between two variables is going to be z phd by z pubs equals this times this, right? Then we can just grab this, drag it down, and now we have the product of all of our z-scores. This product is a representation of the overlap, but it varies across people, so we need the average of that product. So how do we get that? It's actually the average of the summed product. What do you guys think? Everyone take a guess here?
Do you take the absolute value?
Nope, we don't even absolute value this. We don't have to absolute value this. I know what you're thinking, and it kind of looks like when you do the absolute value here, or that you need to do an absolute value or else you're going to wind up with a mean of 0, right? But we're actually interested in the sum of these, not the mean. So how do we get the sum of these? Because remember, it's the mean of the product. So the mean of the product means we have to add everything up. Think of what an average is. You add everything up and you divide by n, or in sample statistics, n minus 1, right? So let's add all of these up. You'll have to forgive me again because I don't know if this is actually what does it, but let's see. I think it does. Sum of 9.9131643 seems about right. What is our n here? Say that again. I think it's 15. So n is 15. So if the correlation is the standardized average overlap between two variables, then we can calculate the correlation by looking at this product, the sum, and then looking at the mean of that product, right? Which means our correlation should be R should equal this divided by this minus 1. What was our correlation? Anybody remember? 0.6 what? 0.657. Let's see how close we get. That's pretty close. So I asked you earlier when we were just starting to tell me to explain a correlation coefficient in terms of math. In terms of the mathematics that underlie a correlation coefficient, who has a simpler explanation of it now? Here's what it is, and this is true for every single regression coefficient, at least every single standardized regression coefficient, which directly translates to unstandardized regression coefficients. But every regression coefficient is the mean standardized product of two variables, or of multiple variables in the case of multiple regression. In other words, you multiply the two variables, divide by n minus 1, and that's what your correlation is every time. They have to be converted to z-scores first. Just so the equation that I showed you earlier, right here, can be simplified into, this won't make it into the video either, sorry. Can everybody see if I write over here? The equation is,
I have a question.
yeah.
So, can we definitely call it mean standardized product, but the division is from n minus 1 instead of n.
Yeah. So in statistics, remember from last semester, in sample statistics, we do n minus 1, which corrects for, what does it correct for? Anybody know? Corrects for bias in sampling, right? If we had a population, then we would just use n. All Pearson product moment correlations use n minus 1. And in fact, almost every single equation that we use uses n minus 1. So. Okay, anyway, we have z of x times z of y summed over n minus 1. And this is so much easier than that, right? And so the way that you can think about this is it's the overlap in standard deviations. That's what that is, right? It's the product of standard deviations divided by n minus 1. Does that make sense? Okay. Let's take a short break, and then when we come back, we will dip back into regression and talk a little bit more about residuals. Sound good? Actually, before we take a break, are there any questions?
Yeah. Where'd the one come from again? Like, how did we get the standard deviation? The one. So I know that to get the z-scores to equal 0, that's just the average of all the z-scores, right?
Yeah, I'm gonna turn this off. Actually, to get the z-scores.
Okay, so it's just this part is like, how did you get the one?
Oh, when you divide that value by the standard deviation, the raw standard deviation,
Oh, okay.
then it sets those things to, then it sets your standard deviation to 1. You already have a standard deviation of whatever that value is, so you're dividing it by that same value. Anything divided by itself
Right.
is 1.
Okay. Okay.
Yep.
Can you repeat what you said about the correlation coefficient? The simpler sort of explanation of it being standardized.
Yeah, it is the mean standardized, the product of the mean standardized product of two variables. Sorry.
But that's equal to the standardized regression coefficient, right? Beta?
Yes, it is equal to the standardized regression coefficient. Indeed, that is an unstandardized regression coefficient or an unstandardized correlation. Okay, I'm gonna stop.